Okay, so today we're going to be doing 7.2, area between curves. So I know we've been doing 5 for a while, so it's in my head. So, you know what was really confusing for me the other day? We were doing 15.4 in Algebra 2 and 5.4 here, so my brain was just not having that. So to find the area between two curves mathematically, you will take the integral on an interval of the top function minus the bottom function. So the reason that I say top minus bottom is you have to graph the function to see, of course, which one is the top boundary and which one is the bottom boundary of that region. There's no other way to do it but to graph it. Okay, so the graphing portion tells you what is going to go first and second in the integration process. Now, sometimes you are going to be given an interval. Other times you have to find the interval based on the actual picture. So if two functions are like crossing over, you're going to see those x values. So step 1 is to sketch the functions to see which one is on the top. Step 2 is if the interval is not provided, find where the functions intersect. These are your boundaries. These are always x values, by the way. I think my pen's in white, so that's not going to help. X values. And then set up the integral and solve. Alright, so the first one we're going to do here says, let R be the region bounded by the functions f of x equals x plus 4 and 3 minus x over 2 over the interval 1 to 4. Find the exact area of the region without using a calculator. So when I say without using a calculator, I don't mean you can't use a calculator to do simple math. I mean like you're not graphing it and then finding the area that way. So basically any of the calculators you guys have on the desks are fine for this. So step 1 is we're going to have to graph these two functions. So I'm going to start by graphing this one. What kind of function is this? Linear, with a y-intercept at 4, and then the slope of 1, so up 1 over 1. And you're going to do a few points until you have enough points to make the line. And then we're going to do the same thing with the other. So what type of function is, I meant to put g of x, but I left it as f of x. What type of function is the other function? How about if I rewrote it like this, and then I factored out a negative 1/2 from the first part? Isn't it also just another linear function? It just has a fractional slope. So not to be confused with anything else. You can tell a function is linear based on its exponent on the x. So, and nothing's in the denominator or anything, so our y-intercept at 3, and then we're going to go down 1 over 2. So you're going to end up with something like this. And then once you have a few points, you're going to connect them with a line like that. Now what you're going to notice with these two functions is there's no natural boundary. That means that they don't cut off a certain area or section. You'll see some that do have natural boundaries. We'll do one like that after. So when there is no natural boundaries, they're going to have to give you an interval. So what that means is from 1 to 4. This is the area between the two functions that we're trying to find. You guys see that? So that's why they have to give you that interval boundary when there is no natural boundary, because you wouldn't know where to find the area, of course. Now that you have that, we're going to set up our integral. So here's how you set up the integral. If they give you the interval, you're just going to set it up with that interval. And now with the boundary, you have to look at the boundary and determine what function is on top of the boundary. Which one's on top of the boundary? X plus 4, right? You guys see why? This one's on the top. And then minus the lower boundary, which is the other function. 3 minus, I just rewrote it as 1/2, same thing. So everybody see why we set it up the way we did? Top minus bottom, always. So then we're going to distribute the negative. We end up with 1x plus 4 minus 3 plus 1/2x. dx. Now I'm just going to combine like terms. So what is 1x plus 1/2 x? 1.5x or 3/2, same thing, plus 1, right? Everybody good with how we got that? Okay. Now we have to integrate. So when we take the integral of x, it's going to become x squared, and we're going to divide by 2. So it's going to be this over 2, x squared, plus, what's the integral of 1? X. From the boundary 4 to 1. So I'm going to do that in my calculator. 1.5 divided by 2. That's 0.75. So 0.75, 4 squared, plus 4, minus 0.75, 1 squared, plus 1. 4 squared is 16 times 0.75 is 12. Minus 0.75 plus 1. That's 16 minus 1.75, which is 14.25. Or 14 1/4. So any questions about that procedure? Okay. Now another thing I want to mention before we move on, you know how when we integrate a large area, or you're given a picture and you got to shade the areas and find it, and anything below the x-axis is negative and above is positive? Mm-hmm. That's the case for what we did in the past, and that's true for a single integral of a single function. But when you're looking at an integral of two functions in the area between them, that answer will never be negative. Okay? Because this is talking about true area between two functions. How much space exists between these two functions? That can't be negative. You can't have negative space between two functions. So even if this was in the denominator, even if this was below the x-axis, this would still be a positive region. Does that make sense to everybody? So it's different than what we looked at in the past, because it's space between two functions. Okay. Yeah.
So like for the test, I don't know how to do that.
So yeah, just be aware, like if I ask you a question of the region between two,
Yeah, it's not gonna be negative.
yes, but if you're doing one where you're given a picture and say find the total integral of, that would be possibility of being negative. So it says let R be the region bounded by the two functions. Find the exact area of the region without using a calculator. What do you notice this problem is missing that the other one had? No boundaries. So that means that this will have natural boundaries, so you'll see what that looks like when we do it. So you all know how to graph functions. You graph them however you want. You can find the vertex, you can plug points in. I am going to start with the y-intercept, which on this function is 6. And this is a quadratic, not linear. So now I'm just going to plug in some numbers around the intercept. So I'm going to plug in 1. So if I plug in 1 here, I get 1 squared times -2 plus 6 would be 4. And if I plugged in -1, it would also be 4, right? Now what if I plugged in 2, for example? What's 2 squared going to be? Times -2? -8 plus 6? -2. And quadratics are symmetric. So it's going to look something like this. Once you have it. Yes. Yes.
Did you say 4? Yeah, you have an eye.
Oh. It's so tiny, it's hard for me to see it.
Miss Russell, none of these calculators work. I think these are all the broken ones.
I meant like behind you on the desk behind you.
Oh.
Yeah, all the ones in there are all the broken ones. I think I graphed this one wrong too. There we go. What a mess. That looks better now. Okay, So now we're going to graph the other function, which is also a quadratic. Now what would be the y-intercept of this one? 0. Because there is no, number added or subtracted at the end. And then if I plugged in 1, what would I get? 4. If I plugged in -1, what would I get? 4. If I plugged in a number bigger than 1, like 2, I would get 8, right? So I can do 8 here and here. And then I keep wanting to go over one more for some reason today. So it's going to look something like this. So do you see what I mean by a natural boundary? See how there's a closed off space between the two functions in this one that the other one didn't have? So that is the space you're finding the area of right there. So you're going to set up your integral. Now what you're going to do is you're going to look at what x values on both sides close off this function. So what x value closes off the function on the left? Good. And on the right? Good. Which function closes off the boundary on the top? Good. And on the bottom? Good.
Can you say that again?
Sure. So this right here is the boundary on the left. This is the boundary on the right. Then it's always top minus bottom. So the function that closes off the area on the top goes first. And then the function that closes off the area on the bottom always goes second and is subtracted from it.
Okay.
You got it? Okay, perfect. So this is going to become -2x squared plus 6 minus 4x squared. These are like terms. So this becomes -1 to 1, -6x squared plus 6. And now we're ready to integrate. So what's the antiderivative of -6x squared? -3x cubed. Isn't it -2x cubed?
Yeah. Never mind.
I was just going with it. I was like, yeah, sounds good to me. It's okay. And then what's the antiderivative of 6x? Now we just plug in our boundaries. Now, if you get a negative answer, you know something went wrong. So that's kind of a good tell that you set up the integral wrong or something isn't working out right. So just keep that in mind. So this becomes -2 plus 6 minus, this becomes +2 minus 6. This becomes 4 minus a -4, which is what? 8. Make sense?
Yes.
Okay. So I know that yesterday when I showed you the schedule, I told you you have time to do your 7.2 homework